integrable. Right? So this is a homework problem for you to do, okay? So if f is in LP space, then f is absolutely integrable over minus pi to pi. All right. And the technique used is exactly the same as we used for p equal to 2, okay, at the beginning of this section. Okay, because we have shown that every square integrable function is absolutely integrable. Right. All right. So this is the case. All right. And so every so with this property, so every function in LP space can generate a trigonometric Fourier series. Okay. Right. So the following. So the following theorem is a striking general result. Okay, on the representation oh, by the way, one and second, second, if f is piecewise continuous, is a piecewise continuous function on minus pi to pi, then f is in LP space. Okay, for all p here. So so for each p you have a big space, okay, and so each LP space contain all piecewise continuous function. Okay, and the proof is also the same as we provided for p equal to 2. Okay. Now, so I will state a theorem which is a striking general result on the representation of trigonometric Fourier series. Okay, so I will state in theorem 11.4.b, and it's called the Carlson-Hunt theorem. So it's Carlson-Hunt theorem. All right, so the statement is like here. The trigonometric Fourier series generated by a function f in LP. Okay. All right. So the reason why such a function can generate a trigonometric Fourier series is because any such function is absolutely integrable. Okay. All right. And so so this trigonometric Fourier series will converge to f almost at almost all x in, okay? So it's very general, right? Except a subset of this interval with length 0. The trigonometric Fourier series generated by f converge to f. Okay, converge at every point, except for points in a subset with 0 length. Okay. Now, how about p equal to 1? Why we exclude p equal to 1? Okay? Why we exclude p equal to 1? Remark. The great mathematician Kolmogorov, right? Kolmogorov found a function in L1, which is the set of such that the integral right? So what is that? What's that? It is the set. L1 is the. Oh, okay, yeah. Maybe I. Okay, which is the set of all absolutely integrable function on minus pi to pi. Okay, so if we consider the set of all absolutely integrable function, okay, then such a function can generate a trigonometric Fourier series. Okay, but Kolmogorov found a function in this L1 space whose trigonometric Fourier series diverge everywhere. Means that for every point on this interval, the trigonometric Fourier series will diverge. Okay, so by construction. Okay, and I also give a paper of the written by Kolmogorov. All right. So of course you can see such an example would be non-trivial. Okay. Any questions? Okay. Okay, so at this point, we basically give the most updated answer to our convergence theorem problem, and as well as the representation problem we asked at the first section. Okay, so this is the best we can do up to now. Of course, there are some special cases that you do have stronger result, but I mean for general results, this is the one we can give. Okay, and for piecewise continuous function, which is a very useful class of function we encountered in practice, we basically give satisfactory answers. Okay, and so you can apply them to your applications. All right, now we would like to apply the uniform convergence and the absolute convergence theorem, means that theorem 11.4.8 to prove termwise integration. Okay, so here is an application of the theorem 11.4.8. We call termwise integration of trigonometric Fourier series all right, so we let f be a periodic function with a period to pi, and piecewise continuous on minus pi to pi, and A0 plus summation n from 1 to infinity n cosine nx plus bn sine ns. Okay, this one be the trigonometric Fourier series. Okay, generated by f. Okay, and at this point we have to give a comment here. So in general, we do not know. Okay, the convergence of this trigonometric Fourier series. Okay, we don't know, because to have a convergence statement or representation statement like in theorem 11.1.2 or in 11.4.8, we require additional property. In theorem 11.1.2, we require that this piecewise continuous periodic function have a left hand and a right hand derivative at every point. Okay, that is for pointwise convergence. For uniform convergence, as well as the absolute convergence, we require that this function f has piecewise continuous derivative. Okay. So if you just say that the f is a piecewise continuous periodic function, and then we don't know the convergence of the trigonometric Fourier series generated by f. We don't know. Okay. But we have the result. But the series of termwise indefinite integral. Okay, like here. For every term in this trigonometric Fourier theory, we construct the corresponding indefinite integral. For the constant term a0, we construct this indefinite integral. All right? And for the other term here, the construction would be the same, x0 to x, and we have ak cosine kx plus bk sine kx and the dx. So of course, this indefinite integral exists, right? For all x in with x0 being any point in this cross interval. Okay, so for every term, we form the corresponding indefinite interval. Okay, so corresponding, right? And so this has come to a series of functions. Okay, a series of functions. Maybe I think without confusion, I should use t. All right, sorry about that. Okay, so I use t here. Okay. Okay. All right. So this series of termwise indefinite integral. So that is a series of functions. Okay. Now this series of functions, right, converges. Okay, converges to the indefinite integral x0 to x f of t and dt. Okay. So this one is also a function of x, right? And because f of t is absolutely integrable over the interval, so again, for every fixed x0, and when we construct this indefinite integral, this integral always well defined. So this series of termwise indefinite integral converge to the indefinite integral uniformly and absolutely. Okay, on the whole interval. Okay. Okay, so in particular, we have equal to plus summation Okay, and now I write the proof. So now since f is absolutely integrable over minus pi to pi, we define a function on minus pi to pi. Okay. So we define a function. So this is f t minus a0 and dt. Okay. Right. So we select from the minus pi to x. Okay. Right. So we define a function. Now, by the first fundamental theorem of calculus, okay, I believe you know this fundamental theorem in last year when you studied calculus. So by the first, the new function f of x is continuous. Okay, so it's continuous minus pi to pi. It's continuous because that we define this function by integral. So when we have integral, then this one should be continuous, right? And f of x has has a derivative f prime x at each point x in the open interval from minus pi to pi in the open interval, where f is continuous. Okay, where f is continuous. So the first fundamental theorem gives us that and for such an x, the derivative is equal to the integrand. Okay, equal to the integrand. So the first fundamental theorem of calculus states that this indefinite integral has derivative, right? Has derivative f prime of x at each point where f is continuous. Okay. So that is the statement of first fundamental theorem of calculus. It is continuous. It is continuous. It is because that this indefinite integral is defined by the integral. So you can prove that directly, right? Okay. But I observe this property into this version of first fundamental theorem of calculus. Okay. So the important thing is that the indefinite integral has derivative whenever the integrand is continuous. And also the point should be not on the edge, on the both ends should be in the open interval from greater than minus pi by less than pi, and f is continuous. And also we know that if for such x, then the derivative, all right, at x is equal to the integrand. Okay, so that is the content of first fundamental theorem of calculus. And from here, so that's all right. So that f of f, all right, the f is all right, and also, and since f pi, okay, f pi is equal to from minus pi to pi, and f of t minus a0 and the dt, which is equal to pi minus pi f of t dt minus pi a0 dt. So this is equal to 2 pi a0 by the definition of a0, okay? The Fourier coefficient a0. So a0 is just 1 over 2 pi of this integral. And this is minus 2 pi a0. So this is 0. And the 0 is also equal to f of minus pi. Okay? And so this is minus pi f of t minus a0 dt. Of course, it's 0. So f pi is equal to f minus pi. Okay? All right, and so we know that. So that, so f of x, so f can be regarded, so f is a periodic function, is a continuous periodic okay? So f is a continuous periodic function with a period 2 pi. Okay. So even though we define this as on one period, but it can extend to the whole real line. And because f pi is equal to f minus pi, so you know we can repeat. All right. So f of x is a continuous periodic function with a period. And has a piecewise continuous derivative on minus pi to pi. Why? Because by the first fundamental theorem of calculus, f prime exists and equal to f of x minus a0 when this function is continuous. Because when f of x is continuous at x, because this is a constant, so the difference is also continuous at x. Okay. And because f of x is piecewise continuous itself, so f of x is piecewise continuous, and it has left-hand limiter and the right-hand limiter. Okay, so you can see that fx has a piecewise continuous derivative. Okay, so you can check the definition. All right, you find that. All right, and so this indefinite integral, all right, satisfy the premise of this theorem, because now we consider capital F, right? So capital F is a continuous periodic function, and the capital F has a piecewise continuous derivative. Okay, okay. So the geometric, so from here, so by theorem 11.4.8, the trigonal metric Fourier series. We call it to be, say, A0 plus summation to infinity an cosine nx plus bn sine nx. Right? So the generated by capital F, okay? So generated by capital F converges to F, okay? So converge to F uniformly and absolutely on the whole interval. The whole interval, okay? Because F itself is a continuous function, okay? Okay, now, so now things, okay? So from our construction there, from there, x0 and f of x, d of x. So for arbitrarily selected x0, okay, in the interval from minus pi to pi. So this one, as we know, this one ft minus a0 dt is equal to minus pi x0, okay, okay. So this indefinite integral can be written in this way, and this is equal to f of x minus f of x0. Okay. Is okay? So we have now we have the indefinite integral is equal to f of x minus f of x0 plus this indefinite integral dt. Okay, so when we look at this one, and we know that this trigonometric Fourier series converge to F, right, uniformly and absolutely. So that so we can see okay, so we can see the series and the series, all right, x0 to x a0 and dt, okay, this one plus the difference, right, and the difference because this trigonometric series converge to f of x, all right, so we can replace to infinity. And we have an, so of cosine nx minus cosine nx0 plus bn sine nx minus sine nx0 together. Okay. So this is just the right hand side. Okay, this is the right hand side. Okay. And in the difference, the constant term has been cancelled. Okay, right? So you see that this part corresponding to f of x, and this part an times cosine nx0 bn sine nx0 is just the f of x0. Okay, so this is just equal to, this is equal to okay, so this one will converge to, okay, so this series converges to a0 dt plus f of x minus f of x0, okay, which is equal to, okay, so this one uniformly and absolutely on the whole interval. Okay. Okay, and we know that this expression is equal to this indefinite integral. Okay, so we have that. So we find a series of functions which converge to this indefinite integral uniformly and absolutely. All right. So the only thing left is to show that this series is the same as the series of termwise indefinite integral. Okay. So, and the first one, okay, we obtain this one, right? The only thing left is here. We will show that this term, this one, is equal to this one. Okay? Remember, the capital AN, capital BN are Fourier coefficients generated by the big F. And here, the little a and little bk are Fourier coefficient generated by small f, little f. Okay, so they are different Fourier coefficients corresponding to different functions. Okay, but we will show that this is the same as this one. Okay. Okay, so we have now to link now for n greater than or equal to 1. Okay, we have AK. So AK Fourier coefficient obtained by capital F. And by integration by parts, we have okay. And remember, f pi equal to f minus pi equal to 0. Of course, sine m pi, sine minus m pi are also 0. So the first term is 0, of course. And the second term, you see here, this is corresponding to the little b n and n here. Okay, so you see that the Fourier coefficients related to the capital F has relation with the Fourier coefficient generated by little f. And similarly, so this is by integration by parts. Okay, so this is integration by parts. And we have bk, the same. Sine nx. So this is f of x cosine nx. Oh, sorry. AMBN. And this is m pi minus plus 1 over m pi. Okay. F of x cosine nx dx. So this is equal to an divided by n, also by integration by part. And f pi equal to f of minus pi equal to 0. Okay. But yep. Or just equal will be enough. Okay. Because of the pi and the minus pi. So yeah, but it's 0. Okay. Okay, so that this is the big A and big B. Okay, and also for n greater than or equal to 1, we have the integration of x0 to x is a n cosine nx dx dt. So let's integrate. Let's see this term. Okay. Okay, and so we have an n and sine nx minus sine nx0. Okay, and so now when we look at this one, so this is Bn. So this is Bn, and sine nx minus sine nx0. Okay, so you see that the integral is equal to this term. So the integral, this integral is equal to this term here. Okay. And x0, x bn sine nt dt is equal to minus bn divided by n cosine nx minus cosine nx0. So that is equal to an cosine nx minus cosine nx0. Okay. Right? So we have established the equality. So this term is equal to the integral of this term. And this term is equal to the integral of this term. Okay. Okay. So we conclude that the series of termwise indefinite integral okay from x0 to x a0 dt plus summation, and from 0 to infinity x0 to x an cosine nx plus bn sine nx. Oh, nt, sorry. dt converges to the indefinite integral. Uniformly and absolutely on minus pi to pi. Okay, so this complete the proof, right? Okay, so any questions? No. Okay, so if no questions, so this is for today. So I'll see you on Thursday.